making our world a better place using data science and geographic information systems. We have Kushi from India, Diana from Hong Kong, and Muhammad from Pakistan. 80% of plastic ocean waste comes from the land. In developing countries, inadequate waste management services often lead to improper use of waterways for trash disposal. Rainwater and wind also carries plastics into rivers and drains and end up in the ocean. Research shows that 1,000 rivers are responsible for 80% of riverine pollution. Smaller rivers account for even more plastic pollution. Therefore, instead of focusing on the largest rivers, we consider the most influential factors to plastic pollution and develop our solution. Most of the top 20 rivers are located in Asia, such as the rivers in India. India alone has roughly estimated to represent an 8 to 9 share of overall losses of total plastics into the environment. Studies estimate that India's rivers dump more than 126,000 metric tons of plastic per year into the ocean, and placing India as the second highest contributor of plastic pollution in the world. Because of this, we chose India as our case study. We used a data science and geospatial approach to map the plastic pollution risk. First, we identified 10 most important factors affecting plastic pollution, figure out the relationship between parameters and plastic pollution, and set the scoring criteria. Then we collected the data and put them in an Excel sheet. The highlight of our solution is the data pre-processing and processing part. We clean, structure, and analyze the data. More will be explained later. After finding the top sites, we further validated the test results with local characteristics. Based on the results, we came up with our solution. In stage 1, we identified almost 1,600 dump sites in India, of which 690 dump sites were from the Global Plastic Watch and 101 dump sites were from the Ocean Cleanup. We collected site attributes from the Global Plastic Watch and metric tons of plastic pollution per year from the Ocean Cleanup. Here is the map showing all of our collected dump sites. We collected the site attributes, and then we generated 3 kilometers buffer zones as the high-risk plastic accumulation zones, where dump sites from both datasets are within 3 kilometers from each other. Eventually, 10 coastal dump sites were identified. We set the third source of parameter of these dump sites, and then we analyzed this as well as the management practices by looking at the satellite imagery. We then collected the data and set the scoring system uniformly for each parameters, and it ranges from 1 to 3. Here is the scoring table for the raw data of each of the 10 sites, and from the right-hand side, you can see dot extension. This means the plastic emissions of each of the nearby plastic emission sites. And then we set the scoring system ranging from 1 to 3, with 3 being the highest score, which means the high risk. Here we can see the red parameters are the parameters that we think they are more important, and we will assign higher weights to them. As for the data processing part, we performed different tests to calculate the final scores for each site. And finally, we used a risk assessment matrix to categorize each dump site based on the total score. We used the analytic hierarchy process, AHP. First, we create a pairized comparison matrix considering the relative importance of parameters. Then we compute the agent factor. We do this by computing the consistency index as well as the consistency ratio. And finally, we obtain the agent factor and we assign weights to each parameter. This is the final weight, being the distance to waterway, nearby water type, population management practices with different weights. And then we calculated the weighted final scores. So from this table, we can see that site 8, which is Mia Bayanda, has the highest scores among all the factors. Therefore, we treat this as our case study. To validate this, we consider different parameters more carefully, such as the distance, landform type, and soil characteristics. And we come out that Mia Bayanda has the high risk of plastic pollution to the nearby water body because it has relatively short distance from the waterway, the landform type, soil characteristics, climate, as well as the moderate waste management practices. For the detailed analysis, we looked into the solid waste management in Mia Bayanda. The solid waste is managed by the corporation, and then they are responsible for the collection, transportation, and disposal of solid waste. For example, we can see that most of the waste comes from households, followed by restaurants and hotels. Here is the pie chart. And then we further find out that the corporation has used the door-to-door collection of waste instead of the recycling bins. And from this, they collected waste from different sources, and then they even segregated the plastic waste, such as from dry waste into plastic, paper, glass, and metal waste. They even proposed a waste-to-energy plan. However, this is just a proposition. From now, all the waste generated are from the dump sites. You can see that from this table, all the waste will be dumped into the dump sites. Therefore, from our estimation, it is estimated that the plastic waste can account for around 10 to 15% of total dry waste generated in urban areas of India. Based on this, it can be assumed that out of 120 TBD of dry waste generated at nearby Anda, around 12 to 18 TBD could potentially be plastic waste. If you assume the average of 15 TBD plastic produced and considering 365 days in a year, then the total amount of plastic produced in a year would be 5,475 tons. Therefore, we can assume that Myanmar can produce around 14 to 20 tons per year of plastic waste entering into the sea, which is significant. Then how to solve this problem? We identify that the problem is that Myanmar has the waste management practices that is mainly landfill. Therefore, we suggested that we should segregate the plastics at source. To do this, we recommend we should collect the dumping of plastics in a closed site. And we further educate the public by introducing the education campaign in the door-to-door collection of waste. So this, we can segregate at source by educating the public to separate the plastics from the different waste. And then we can collect the waste from door to door effectively instead of letting the waste dumped improperly on the streets or into other sites. And then this can also reduce in plastic emission. The implementation of the system can help reduce plastic emission as the waste will not be left to accumulate and degraded in the open landfill. This can also help create job opportunities for locals. According to our research, about 81% of the population of Myanmar is educated. This implies that our education campaign could be impactful. First, it can create high awareness among the citizens because they are more likely to understand the consequences of their actions and change their behavior. Besides, with the high literacy rate, people are more likely to understand the importance of waste segregation. Lastly, educated individuals are more likely to have the skills and knowledge to participate in waste management initiatives, such as holding cleanup drives. Overall, having a high percentage of educated individuals in Myanmar can be a significant advantage in addressing the plastic waste pollution problem, as it can create a positive culture of environmental awareness and actions. Lastly, once the waste is segregated and collected, the waste should be stored in a closed sites to prevent the open decomposition of plastic into microplastics or other materials.